All right. Hello, everyone, and welcome back for our part three, the final part of One-Way ANOVA. In this lecture, we're going to be going over the second example, which will be a significant ANOVA, a statistically significant ANOVA, which is going to require us to do a couple extra things. But before I do that, really quickly, I want to go back and correct a quick mistake that I made in the previous voiceover lecture. So if we remember back to our question about IQ in Pennsylvania, California, and New York, I had listed in the APA style conclusion the mean squared error as 854, which was incorrect. It's 854 is the sum of squares within. What we want is the mean squared within. Sorry about that. I listed it as 854. What we actually want is 854 divided by 12, which is 71.17. So that's what we want to list in the, here we go, in the APA style conclusion. 71.17. So now we can move forward for example number 2. And remember, example number 1 had a non-significant result, meaning that the groups were equal. We failed to reject the null. Pennsylvania, California, and New York had equal IQs, right, from people coming from those states. So now in example number 2, what we're going to see is a statistically significant example. And this statistical significance is going to actually complicate things just a little bit for us, such that we have to do some extra work, some extra statistics. So let's set up our research question. We want to know, does information about the prior criminal record of a defendant influence ratings of guilt by a jury? So ideally and theoretically, the way it should work is that people are judged by the current evidence in front of them and based on their current behavior. However, some psychologists, some legal psychologists, are interested in whether knowing that a defendant has had a prior criminal record or not had a prior criminal record, does that information influence a jury's decision, even though it sort of quote unquote shouldn't influence their decision? This is actually a really interesting area of study in psychology. Things like eyewitness memory, jury selection, the legal process is full of sort of instances where psychology can come into play. And there are many, many people across the world who study this stuff. It's actually really, really important. So I digress. Our research question is, does information about prior criminal record of a defendant influence the ratings of guilt by the jury? So jurors are asked to rate their perception of guilt about a defendant based on whether that defendant had a prior criminal record, a clean criminal record, or we have no information about that defendant. So this lends itself to a one-way ANOVA because we have 3 groups. We have prior criminal record, clean criminal record, and a group of people about which we know nothing, no information. That's our control group, so to speak. So again, just as before, our null hypothesis is that all 3 of these groups are equal, right? Group 1 is equal to group 2 is equal to group 3. And our alternative or our research hypothesis is that there's a difference somewhere. We're not sure where it is. We're going to hope that the ANOVA and then the subsequent post hoc tests can help us determine where this difference lies. We have our 3 populations. Population 1 is defendants with a prior criminal record. Population 2, defendants with a clean record. Population 3, defendants with no information, right? We are oblivious to their criminal record prior. So I'm going to sort of wave my hands and do all the math that we did in example 1. If you need a refresher on that math, go back and watch part 2, which was example 1 for the math. But here, what we're going to focus on is what's different from a non-significant ANOVA, which is what example 1 was, and a significant ANOVA, which is our example here. So just to sort of orient ourselves, we have our 3 groups: criminal record, clean record, no information. We have ratings of suspected guilt by our juries. We found the means for each group. We found the sum of squares for each group. And then using the calculations from the last video, we found the sum of squares between the sum of squares within. We found our mean squared between, our mean squared within, and then we found our F value. As it turns out, this is a statistically significant result. And so what we're going to focus on from here going forward is what would you do if the ANOVA is significant? So our first example showed what we would do if the ANOVA is not significant. Basically, we stop right after we find the F value and the critical value. If the F value is lower than the critical value, then we stop because it's not significant, and we write our APA-style conclusion. However, here we have a significant F value, 4.06. If we go and look at our F table for our critical value, with a degrees of freedom between of 2, a within degrees of freedom of 12, and an alpha of 0.05, we have a critical F value of 3.89, which means that our F value of 4.06 is statistically significant. So if we're statistically significant, what that means is now we have to answer 2 new questions. First, what is the magnitude of this difference? That's an effect size, just like we had with the t-test. What is the magnitude of this statistical difference? And then number 2, where does this difference occur? Because we have 3 groups, group 1, group 2, group 3. The ANOVA tells us simply that a difference exists somewhere between our groups. It doesn't tell us where. It doesn't tell us which groups differ from which other groups. That is not information that's included in our ANOVA. The ANOVA simply says something is happening here. I don't know what, but something is happening. So we need to understand the magnitude, and then we need to understand the the location of the difference, if you will. So if we want an effect size within ANOVA, we have to calculate what's known as a partial eta squared. Cohen's d is the effect size for a t-test, but we need a different effect size, partial eta squared. It's denoted by this symbol here. That's the Greek symbol eta squared. The calculation is really simple. Eta squared equals sum of squares between divided by sum of squares total. These are things that you would have calculated previously in your big ANOVA table, as we discussed in example 1. Again, here, we're sort of fast forwarding. I'm giving you all of that information. You might want to go ahead and write this stuff down on maybe a piece of paper so that you have it with you. Press pause, perhaps write down all this information, because we're just going to fast forward through the math. If you need help with the math, go back to the first example and or reach out and get help. But wave a magic wand. I did the math for you, and we say that this is significant. So the first thing we need to do is take our sum of squares between divided by our sum of squares total. That ends up being 0.4. 0.4 is a large effect size for an ANOVA. Here's roughly our way of denoting effect size. 0.01 is anything around 0.01 is small, anything around 0.06 is medium, anything around 0.14 is large. So that means 0.40 is quite large. This is a really robust effect. So what this tells us is that the difference is substantial. We have a substantial significant difference here. So that's our first step after understanding statistical significance. Our next step is going to be to try and locate the difference. So remember, the ANOVA, the F ratio, is an omnibus test or just an overall test that does not tell us where the difference lies in our experiment. Is it 1 versus 2? Is it 1 versus 3? Is it 2 versus 3? Is it all of them against each other? We don't know yet. All we know is that a significant difference exists. So what we have to do is we have to delve deeper and we have to see which specific differences exist. To do that, we use what are called post hoc tests, specifically a Tukey HSD, honest significant difference. What we're going to do here is we're going to do every iterative comparison possible from the ANOVA. So if we have 3 groups, that's 1 versus 2, 1 versus 3, and 2 versus 3. If we had 4 groups, it'd be 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, 3 versus 4, so on and so forth as we add groups or levels of the independent variable. The point here is that after we have found a significant ANOVA, we need to do individual comparisons such that we find the exact nature of the difference. We do this by computing Q's. Q values come from mean differences in the numerator. So if we're doing group 1 versus group 2, we would do the mean of 1 minus the mean of 2 divided by the square root of the mean squared within divided by n. In this case, I'm sorry for the difference between big N and small n, but in this case, n is the sample size within each group. So we had 1, 2, 3, 4, 5 individuals within each group. So to calculate a Q, we would do the mean of group 1 minus the mean of group 2 divided by the square root of the mean squared within divided by 5. Order of operations, right? Obviously, you do mean squared within divided by 5. Then you take the square root and then you do a fraction, right? This difference divided by whatever your denominator was. So what does that look like for each of our comparisons? Let's take the first comparison, which is group 1, the criminal record group, versus group 2, the clean record group. Well, the mean of group 1 was 8. The mean of group 2 was 4. So the numerator of our Q test, our post hoc test, is 8 minus 4. Our denominator is the square root of 5.33 divided by 5. Now, let's backtrack and figure out where these numbers come from. 5 comes from the fact that we have 5 individuals within each group. So that's our little n, actually. So the number of individuals within each group is 5. 5.33 comes from a thing that we didn't calculate here. Let me stress that. We did not do this calculation. I'm giving it to you to sort of fast forward ourselves through this problem. But 5.33 comes from our mean squared within, which is the denominator of our F statistic, which you would calculate if you did this all by hand, as we did in example 1. So again, if you need a refresher on the math for how to do all of this by hand, go back to example 1. But our mean squared within is basically the cumulative sum of squares for each of our groups divided by the degrees of freedom within, which is big N minus K. So 64 divided by 12 in this case gives us a mean squared within of 5.33. So the square root of 5.33 divided by 5. So 5.33 divided by 5, we take the square root, it's 1.03. 8 minus 4 gives us 4. So 4 divided by 1.03 gives us 3.88. So all we've done is this formula for group 1 versus group 2. Then we do it for every other possible comparison. So if we did group 1 versus group 2, we do it for group 1 versus group 3. Then we do it for group 2 versus group 3. And that's all of our possible comparisons. So I would go ahead and press pause here, take a look at where all these numbers come from. Right? The numerator is just the mean difference between whichever two groups you're comparing. And in fact, the denominator stays the same, 1.03 for each of these, because the denominator is simply square root of the mean squared within divided by the number of individuals within a group, little n. So go ahead and press pause, take a look at these numbers, and make sure you know where they come from. Remember, this all reduces to 4 divided by 1.033, or 1.03, 3 divided by 1.03, and 1 divided by 1.03. Okay, so we have our Q values, which we've calculated. Now we need to make a decision about which of these Q values are significant. For that, you guessed it, we need a Q table, which will be provided on iCollege. So at this point, you will have a T table, an F table, and a Q table, and you'll need to be able to use all of them effectively. What the Q table does is it tells us what the critical Q value is for these post hoc comparisons. It's very similar in usage to our F table, because along the left-hand side, we use our within degrees of freedom, which was 12, because we again had 15 participants across the whole experiment, minus K, which was 3 for 3 groups, so 15 minus 3 is 12. So we're using this 12 row. We then had 3 groups. Notice that the top here is K. K equals number of treatments. We had 3 groups, right? Criminal record, clean record, no information. So 3. And so we find the cell of 12 and 3. And on the top is the critical value if our alpha was 0.05, which we're going to assume it was. On the bottom of that cell is if the critical value was 0.01. If alpha was 0.01, this is our critical value, 5.05. So we found our within degrees of freedom, which is 12. We found our number of treatments, which is 3. This gives us this particular cell to work with. On the top is our critical value if our alpha is 0.05. On the bottom is if our critical value, if our alpha was 0.01. In this case, we're going to say that our alpha was 0.05. So 3.77 is our critical value. We're going to take 3.77 and we're going to compare it to each of our Q values. And the same logic applies. If our Q is greater than the critical value, then we reject the null and that difference is significant. If our Q is less than the critical value, as in the second and third comparison, then we fail to reject the null and those comparisons are not significant. So what ends up happening here is that we compare 3.88, 2.91, and 0.97. Those are our Qs, right, for group 1 versus 2, group 1 versus 3, group 2 versus 3. We compare each of these Qs to 3.77 on the table. And so we find that only the first post hoc test is significant, right? 3.88 is the only one that's greater than our critical value. So our ANOVA was significant, and then our post hoc tests tell us that the difference that is actually significant is between group 1 and group 2. That's the only Q that's larger than our critical value. The other Qs, because they're less than our critical value, are not significant. So what the post hoc tests tell us is that these comparisons are not significant. 1 versus 3 is not significant, and 2 versus 3 is not significant. So the only comparison that has a Q value higher than the critical Q value is 1 versus 2. Let's go back and think about group 1 was the criminal record group. Group 2 was the clean record group. So what this tells us is that having a criminal record increases the jury's opinion of guilt when compared to individuals that have a clean record. So what this test tells us is that juries are biased, essentially, right? This would be a problem in the legal system, that simply having a prior criminal record causes a jury to think you are more guilty of the current crime, whether or not the current crime has anything to do with your prior criminal record, right? Having a criminal record at 17 or 18 has nothing to do with the current situation if you're 40 or 45, right? This is a bad thing. But we would need to know as psychologists that this is happening, that juries are biased against individuals with prior criminal records. They are rating them as more guilty when compared to individuals with clean records who they're rating as less guilty. But this is the only significant comparison. Because if we compared group 1 criminal record to the no information, or if we compared the clean record to the no information, those comparisons were not significant, right? Those were these two, 2.91 and 0.97. Those are lower than our critical Q value, 3.77. So what this has told us is that juries treat individuals with a criminal record differently than they treat individuals with a clean record. And that's where our difference lies. So we now need to construct a APA style conclusion based upon these results. The first thing we do is state the test. A one-way analysis of variance, and one-way ANOVA, was conducted to examine whether ratings of guilt were impacted by type of prior information, right, about the defendant. The ANOVA showed a significant difference here we have our statistical statement, F degrees of freedom between, comma, degrees of freedom within, equals 4.07. Mean squared of the error, which is our our denominator of our F statistic, 5.33. P was less than 0.05. We list our partial eta squared, which was 0.40. Now, you are not going to be able probably to produce this symbol, for example, on your exam or maybe in your homework. You can simply type out eta squared or partial eta squared using words to convey this information. So we gave our statistical information to show that the ANOVA told us that there is a significant difference somewhere. Then we follow that up with our post hoc tests. Tukey, honest, a significant difference post hoc analyses revealed that the criminal record group, who had a mean of 8 and a standard deviation of 2.12, significantly differed from the clean record group, who had a mean of 4 and a standard deviation of 2.24. P was less than 0.05. This suggests that people rate someone with a previous criminal record as more likely to be guilty than someone without a criminal record. Thus, previous criminal record increases a jury's ratings of guilt. So, we stated our test and our research question. We gave our significant ANOVA results. We then gave our statement of which Tukey post hoc analyses were significant. Remember, these standard deviations come from our calculations earlier in the problem. If you have the sum of squares for the criminal record group, you can find its standard deviation. If you have the sum of squares for the clean record group, you can find its standard deviation. And then we provide our take-home message. Okay, so that's it for our one-way ANOVA examples in the lecture. What you see here are 2 practice problems that you need to sort of, using the previous voiceover lectures, I would sort of take some time to walk through those previous lectures step by step as you do the calculations for each of these practice problems. Try them for yourself, and then posted on iCollege will be the walkthrough step-by-step voiceover solutions to each of these problems, just as we had with our t-tests. So make sure that you use the last 2 videos to help you walk through practice problem 1 and practice problem 2, and then give them a try, and then watch my voiceover calculations of the correct answers to double check what you've done. That's it for One Way ANOVAs. Thanks for listening, and I will talk to you next time.